Here's a laminated strip made of two different materials. The green layer has a larger thermal expansion coefficient. The red layer has a lower thermal expansion coefficient. When I hit play, the temperature will ramp up from 300 to 400 K, and we'll watch how that affects the structure we've built. The width of the strip is exaggerated compared to a lot of systems that would behave this way, and the reason is just so that you can see the lateral structure on the screen. You can see the strip curls. Strain's shown by the saturation of the color, so the red and green at the end of the strip are in the middle of the scale. They're unstrained. The red and green in the middle of the strip, the red is stretched and would like to pull in. The green is compressed and would like to push out. We'll let this repeat again. So you can see the strain here. And an interesting thing is that the strain stays pretty well equalized at the ends of the strip. It heals out very easily because you don't have the strain's forces don't have to move very much material. But near the middle of the strip, you've got to move all the mass of the remaining strip outside that point quite a good distance. So it takes a long time for the strains to heal out, much longer near the middle of the strip than near the ends, where strains stay pretty balanced. That's something we didn't understand until we built the whole model and we were verifying it. The whole model is built up by dragging and dropping these components, the little dark circles and these green and red lines. What's inside the components is equations. So here are the state equations for one of these. The model is made up of mass points and sections that enforce a Young's modulus. So we've got a temperature, we've got a K, which stands for the elasticity, the Young's modulus. We have an equilibrium length. The length, then we have some state equations. The length is, instantaneous length is just given by the Pythagorean theorem. The length at a given temperature is this formula here, this equation. And these aren't for decoration. This is what actually defines the behavior of each green component. So this is the equilibrium length at a given temperature times a formula for the temperature variation of the rest length of the spring. This is Hooke's law, and that's why they behave like little springs. The rest of these transfer the forces on the spring to the masses at its ends, so we can interconnect masses and springs using those. And I can see all these same expressions for every component in here. And you can put in whatever formulas you like, and then you connect those things up, you drag them and drop them, and eventually you've got a model that behaves like this. You can get some insight. And that's the bimetallic strip. Thanks for watching.